Hello, my fellow engineers. Welcome to Fastware. I do apologize for my voice. I'm a little sick this week, but I wouldn't want to forgo an episode just because of that. So today we're going to be looking at how to measure your application's performance, how to choose a good baseline, and to measure incremental improvements in your application and to understand the noise in your measurement. So a few topics to cover. And for this, I chose a string to int algorithm to illustrate the whole point, as it is very noisy and there is plenty of improvement to be had there. So I'm not going to dive too much into how I'm going to be measuring every little bit. Suffice to say that I have 1,000 generated integers in string form, which the benchmark will run through. So we're going to be measuring 1,000 of the time in order to reduce that noise in a measurement. The overhead of the actual benchmarking tool. So for that, I chose a Geeks for Geeks write your own ATOI algorithm. So just copy it from this link right here. If you fancy to give it a go yourself, you can follow with your starting point there. And this algorithm is fairly primitive. So it comprises of two separate parts. You have the isNum function, which most likely going to be inlined. So what it does, it actually given a character, it checks that the ASCII range is between 0 and 9. And because in the ASCII tables, you can find that 0 to 9 are consecutive values, so only the basic range check suffices here. So this algorithm starts by taking a string to be converted. Initializes the result, the sign, and then checks if the string, beginning of the string starts with a minus and flips the sign to negative. Now, starting there, so we have the basic meat of the algorithm here. So the string starting from I checks if it hasn't reached the end yet, and then checks if that character in that string is a digit, a num, and if it is, it takes the character minus the ASCII character 0, which offsets the entire set from 0 to 9, takes the previous result, multiplies it by 10, and then adds that character. So the algorithm is trivial. Of course, at the end, it multiplies the result by a sign. So we don't know how good or bad this algorithm is. So let's run our little benchmark. As I said, Geek for Geeks ATOI. What we have is 1,000 strings, and we just iterate every single one of them, converting them to integers, and verify in debug mode if value that you converted is the same as it was generated. This is important for you to make sure that you produce the correct output for your input. So let's run this little benchmark and let's have a look. So here we have reached the output, and we have for this algorithm running for one character integer, so a single number, 2 numbers, 3 numbers, 4 numbers, 5 numbers, and up to 10. So these are the mix of both positive and negative. So we can actually look at the output. So it ranges from about 6 microseconds to about 15. But then the question is, do these numbers actually mean anything? It takes some time, but relative to what? I mean, is it good, bad? I don't know. Do you? So we need to do a little work here. This is where we want to choose our baseline. So I know that a standard library implements the ATOI algorithm itself. So here will be our very first baseline. The benchmark here does exactly the same as the Geeks for Geeks one. And let's run the ATOI and see if we do better with this trivial implementation or worse. So let's build and run. Here. Now we completed our benchmarking and we can see some interesting results. We can see that we actually, with our naive implementation of ATOI, do much better than a standard algorithm one. Of course, not entirely true, since the standard algorithm also supports hex values and many more. But let's start there. We can see that actually the standard algorithm implementation takes much, much longer. But we also know that it is not particularly well optimized for input. It has been a standard algorithm since the 60s that has been carried in standards, and nobody tried to improve it. But I do have a compiler which supports C++17, and there I know that there is a much better algorithm, the from char's implementation in a standard algorithm. So let's have a look at it. So here will be our second baseline from char's, and it has slightly different form factor. So here you pass the beginning and the end pointers and a value as a reference. So let's enable this baseline, compile, and run. So now it is finished, and we can see that from char's, this modern algorithm does much better job at actually solving our problem. At smaller scales, 1, 2, 3 characters, it does better than our naive implementation and much, much better than the standard ATOI algorithm. However, I think you can see by now that both our algorithm and the ATOI and from char's have quite a bit of variation from run to run. And this is the noise in the measurement. So what we want to do in order to ensure that our implementation stands up to the scrutiny is to run for a longer period of time and take the minimum for each of these algorithms in order to achieve the best result. Because the longer you run, the closer to minimum you will get. The average, because you don't care about the average of the algorithm, you care about the fastest possible time that you can achieve with a specific algorithm. So what we want to do is we want to improve our basic naive algorithm with something that accounts for basic math and algorithmic properties. So let's start there. Now, taking the Geeks for Geeks algorithm as a template, I started there. So I again initialize the result in the sign, flip the sign as the previous algorithm, but here is the difference. What I do is I cast the character to UN8, right? So UN8 is a char, so this is now an unsigned char. Now, taking a char value of 0 and minusing might produce some modulus arithmetic by overflowing and to negative and shifting everything back to the high bits. So this line and the modulus arithmetic that it entails will only produce a correct output for C only if str value is in the range of 0 to 9 in the ASCII character. So here, as we minus the 0, and our validity check is that C is from 0 to 9, only those values will be permitted by this modulus arithmetic. And the increment does exactly the same as initialization, just with the plus plus. Now, the rest of the algorithm is fairly straightforward, as we have a res times 10 plus the C. Now, the main difference here is that the main body of the loop doesn't have an additional if statement. The only conditional is this C less or equal to 9. So the good and the bad about this is that we only need one check, but the bad is that we need to check again before we return. We might have encountered a letter, not a number, but we also might have encountered the end character. So once the main body of the loop finishes, we need to check that the string has reached the end, and if it did, we know that we didn't encounter any errors. And we can return the result times sign. Otherwise, if there was an error during the loop and it finished early without reaching the end, we'll be returning 0. So with this algorithm now described, let's build it and run it. Now, as it is finished, let's have a look at our result. We can see that we, on a small scale, do much better than the trivial naive implementation. But on a larger scale, we do approach close to what the previous algorithm was doing, the basic geeks for geeks. So we can actually surmise that we have less overhead at the beginning, but the basic loop structure is still in place, and therefore the cost that we pay in multiplying and data dependencies is still there, as we had with the basic implementation. However, we can clearly see that we do much better than std from chars and std ATOY implementations, so we can be quite happy that it is fairly decent implementation, and we do actually quite well here. However, I'm not particularly happy with the larger part of the integers, because most of the integers that you will be dealing with will be small, so this will be fine. However, if you're transmuting hashes of values through the network, and the hashes will be occupying either the full integer or the long, we know that this algorithm and all of these algorithms will scale towards the worst case. So we need to look at maybe a better performing algorithm on a large scale. And we can give it a shot here. So taking as a template the previous algorithm, we do a little improvement here. What we'll do is we'll create a table of powers of 10. So this is from 1 billion all the way to 1. There's 10 integers here. Now, this powers of 10 array size will produce 10, as it is the size of the entire structure divided by the integer. We acquire the char count that we'll have by taking the end pointer minus the begin pointer, so we'll know how long is the string. And then to adjust the scaling, what we will do is we'll take the powers of 10 array size. So here it might be 10. And if we have, for instance, 6 characters, so 10 minus 6, we'll start at the index 4. So 0, 1, 2, 3, 4. And we'll start by multiplying our first character by this, a next character by this, the next character by this. Therefore, now the data dependency will flip backward. So we have a standard multiplication and addition without having parentheses surrounding the entire expression. So how this algorithm works. So as usual, we rely on our modulus arithmetic here. However, our for loop no longer has an expression here. So what we will do next is we actually check if our C is in range, and if it is not, we break out of the loop. And given the result, we're just taking that C, multiplying by its power, and adding to the result. So this expression is the important part here, because that results in only addition, which is associative and commutative, means it can be done in any order, and therefore processors know about it, and they can do this operation, this addition, over multiple ranges in parallel. So it's data level parallelism that actually helps us here. However, we can see that we have some additional cost by doing some basic math at the beginning. So my general assumption will be that the few first characters, maybe first 4, 5, or 6, will be slower, but then we'll start inching through with a better implementation of this algorithm at the higher scales. So let's give it a go and see. Let's build and run. And now it is finished. And we can look at our results. So what we care to compare about is our previous implementation of ATOI and the new implementation. So looking at the results, the previous implementation with 10 characters was about 13 microseconds. This one takes about 10. Here we had 10. That's 10 as well. Here we have 9. That's 10 as well. So we can see that we do a bit better on a higher order of characters. So we actually above 6, we're doing much better than here. Even above 5, we're doing much better. So for long integers, longs, and signs, this implementation would do much better to solve our data transformation problems here. And if you're transmuting a lot of hash values over a network, which will be probably longs or size t's, you can actually save a fair amount of time by writing your own algorithm, which utilizes data dependencies or reduces data dependencies and utilizes data level parallelism. So this benchmarking tool, you can pass additional argument such as benchmark min time and passing a value. So each of these, for instance, to be run for 5 seconds. If I could spell benchmark min time, and it will be collecting the performance characteristics over a longer period of time, which will produce much more stable results. Now, I'm not going to continue running that. I have collected such data earlier, and here are the results. So we can see a decent performance improvement from our baseline for both my STR, my ATOI, and my ATOI 2. So we can also see that we crossed over above 5 characters, where my ATOI 2 becomes much better for larger integers to be parsed from strings. And the relative performance improvement as well shows us that we made a good choice with this algorithm. So I hope that you enjoyed this short demonstration about measuring the applications or algorithms performance, understand a little bit about baselines, understand how to do incremental improvement and measuring incremental improvement at different scales, It's very important to measure your problem at different scales to understand how it does in the whole range of your input and not only for a single integer. And averaging out these will not give you very good results. So if you enjoyed all of that, please subscribe, leave a like, and I hope to see you in the next one. Thanks.